Hello, welcome. In this short video, let us look at filtering of long data sequences. Specifically, we will study about the overlap save method. So recall that the filtering of long data sequences can be described by this block diagram. That is, the first step is that long input is basically segmented into blocks of uniform size, and then we apply the DFT algorithm. We get the DFTs of these blocks, and then we multiply these DFTs with the DFT of the filter impulse response, that is h of k. So the product of h of k and xm of k gives us the output blocks, that is in frequency domain, and then we apply IDFT, we get the output blocks in time domain, and finally we do concatenation to get the signal y of n, or the convolution output or the filtered output y of n. So in this video, let us look at the specific method known as overlap save method for this operation. Overlap save method. So this block diagram, this diagram basically illustrates the overlap save method. Basically, this long box represents the input sequence x of n, each of in which we have L segments of length L. That is, each segment has L data values or L samples. So then we divide them into blocks of each of dimension n. So here the length n is actually equal to L plus m minus 1. That is, for example, for the first one we have m minus 1 zeros, and then L values coming from the input, that is from here. And then for the next block, that is for x2 of n, we have m minus 1 values borrowed from x1 of n. That is, the last m minus 1 values from x1 of n are borrowed to the first m minus 1 values of x2 of n, and then L new values are taken from x of n. Similarly for x3 of n, that is, process will continue. So that means basically we are borrowing m minus 1 values from a previous block, and that means each block has L new values and m minus 1 old values. So this n basically signifies the length of the DFT. That is, for each block we will apply this n point DFT. That is why we have n is equal to L plus m minus 1. So let us look at the specific structure of the input sequence. So again, given the sequence x of n, the first sequence, that is the data blocks, the first block will be x1 of n, which will consist of the following numbers or following values. The zeros for the first m minus 1 terms will be simply zeros, that is m minus 1 values, and then we have x of 0, x of 1, and so on up to x of L minus 1. That is, the first L values from the input sequence x of n are sent to this x1 of n, that is the first block. So the first block has only L actual values and 0 dummy values, m minus 1 dummy values or m minus 1 zeros. And then for the second sequence x2 of n, or the second block, we have last m minus 1 values from the first sequence, that is x of L minus m plus 1, and so on up to x of L minus 1. And then we have new values, that is x of L plus 1, and so on, and the last value will be x of 2L minus 1. So that will be the second block. So these are m minus 1 old values and L new values. And final, and the next x3 of n, a new block, will consist of the elements x of 2L minus m plus 1, and so on, and then x of 2L minus 1. That is the last m minus 1 values from the second block, and then we have new values coming in, that is x of 2L, and so on up to x of 3L minus 1. Again, these are new L new values, and these are m minus 1 old values. Thus we can construct all the individual blocks or segmentation of the x of n. That is, we can process x of n and extract these individual blocks, each of length n. Now when we come back to this block diagram of the long data sequence filtering, so we are able to extract these input blocks which are given by these blocks. So the next step is to extract DFT, that is apply DFT on these input blocks, and then we'll get this xm of k. So the next step is apply DFT on input blocks of n. So to get xm of k, so the next step is to multiply with the DFT of the impulse response of the filter. That is, we have to multiply with the system function of the filter. So the frequency response of the next step is to multiply this xm of k's with the frequency response of the filter. That is, if h of n is of length n, then we directly apply DFT on h of n. So h of n, we apply DFT, we get our h of k. If h of n has a length less than n, then we append sufficient amount of zeros and then we apply DFT and we get h of k. So then once we have h of k and x of m, that is xm of k, our next step is to multiply. That is, we multiply them. That is, ym hat of k will be defined as xm of k, that is the DFTs of the input blocks, and hk, that is the frequency response of our filter. This is the mth block of the output, and the values of k are from 0 to n minus 1. So the next step is to apply IDFT. That is, if you go back to the block diagram, we have ym of k, and now we have to apply IDFT on these output blocks. So that means we apply ym of k hat goes through IDFT. We get our input, we get our output blocks ym of n hat, that is ym of n hat. These are the output blocks. So this ym of n hat as n values, that is capital N values, that is ym hat of 0, ym hat of 1, or ym of 1 hat, and so on up to ym of n minus 1 hat. That is, there are n values in this inverse DFT sequence, that is in the time domain output blocks. Now, so here the main thing we have to understand is that the first m minus 1 values of ym of n hat are influenced or corrupted due to aliasing. So they must be discarded. So the output, the required step is to discard first m minus 1 values. So because if you go back to the original segmentation of the input sequence, we can clearly see that the m minus 1 values for the first block are basically zeros, and the first m minus 1 values of second block are borrowed from the previous block, and so on. So that means the DFT, that means the filtered output corresponding to these m minus 1 values, is basically influenced by aliasing. That means they will be similar to the they have a relation to the output from the previous blocks. So we need to discard them. Since the length of this output block ym of n hat, that is the length, since the length of ym of n hat is equal to capital N, and then we discard the first m minus 1 values. So the leftover, that is the whatever is left, that is we call it ym of n, which will consist of the values ym hat m, and then ym hat m plus 1, and so on up to ym hat of n minus 1. That is, it will consist of the values corresponding to the actual, that is a filtered output corresponding to the actual input block of length L, that is from x of n. In other words, ym hat of n will be equal to ym of n for only values of n from m to capital N minus 1. That is, we discarded the first m minus 1 values, and then we are left with the L values, that is from n is equal to m to capital N minus 1. So these values actually represent the output of linear convolution or linear filtering, and this will be similar to the values, or actually same as the values when we do normal convolution, that is without any segmentation. So this is the required output, and then we concatenate all these blocks or all these output blocks to get the final sequence y of n. That is, when we go back to this block diagram, we get this ym of n, so we concatenate them to get our required output y of n. So that is the output y of n when we do filtering of x of n. So to summarize, in this video we have looked at the filtering of long data sequence, specifically using the overlap save method. So this is the block diagram for filtering using filtering of long data sequences using segmentation and concatenation. So, and the DFTs, of course. So that is by using segmentation of the input into blocks of equal length, and then we apply DFT, and then we multiply this DFT with the DFT of the impulse response of the filter, and then we get the output blocks, and then we segment, then that means we apply IDFT on these output blocks, so we get them in time domain. That is, these are the output blocks in time domain, these are the output blocks in frequency domain, and then we concatenate these output blocks to get the actual output sequence. Now for the overlap save method, the main idea is the input sequence is segmented into blocks of equal length. So the first m-1 values usually come from the previous block. So for the first one there will be zeros, and the second block, the m-1 values, that is the first m-1 values, are borrowed from the previous block, and then we continue the process. So the second step, this is the representation of these input blocks. So the first values are m-1 values, are either zeros for the first block or the last m-1 values for the second block, and so on. So, and the second step is, next, once we have these blocks, we apply DFT, so we get xm of k. That means with the DFTs of these input blocks, and then we apply DFT on the impulse response of the filter, and that means we get h of k, and then we multiply these two, we get our ym of k hat. This means this is basically the DFTs of the output blocks. So once we apply IDFT on these values, that is ym of k hat, we get our ym of n hat, and these are the output blocks, but these have length n. So what happens is, for the first m-1 values of ym hat of n, so the first m-1 values of ym of n hat are basically corrupted due to aliasing, because we have borrowed m-1 values, that is first m-1 values from a previous block for the input. So the output also will have that influence. So we have to discard those m-1 values. So we are left with L values, and these L values correspond to the output of the linear convolution with the L values from the input. So that means they will be part of the actual output sequence. So once we have this ym of n, we just concatenate them to get the output. That is, we concatenate them to get the output sequence y of n. Thanks for watching.